Hey, good morning, everybody. My name is Laura Edwards, and I'm the state climatologist for South Dakota with SDSU Extension, based out of Aberdeen in the northeast part of the state. And I'd like to welcome you today to our first day of our 3-day virtual workshop that we call Climate 201. Maybe a little more in depth into some climate-related topics that we sometimes don't get to address or get to think about. And I'm one of the lead investigators and one of the leadership team for the North Central Climate Collaborative. So we started in the North Central region with all the institutions that you see on the screen there, covering 12-state region. And I like to also call out Hans Schmitz, who's been on the leadership team since the beginning. Also involved has been Peter Tomlinson and Kathy Gale at Kansas State and Nebraska, University of Nebraska, initially with Tyler Williams, and now with Ashley Mueller and others. So we've been working together as a team since about 2015 or so. Thanks to sponsorship with the North Central Region Water Network. And this workshop here today and this week is kind of our first event that we're holding under a new USDA SARE grant. So this is kind of starting a new phase for us with the North Central Climate Collaborative, or NC3 as we call ourselves. So we're so glad that you guys can join us today and this week. We have a great slate of presenters. We tried to build in time for question and answers and some breaks along the way. So hopefully we're not having too much of a marathon session each day. So our agenda for today, we have 4 speakers, 4 presenters. 2 in the morning, 2 right away here, and then we'll have a break around 10:20 Central Time, and then we'll have 2 more to end the day up at noon Central. So that's kind of our schedule for today. I'd like to invite you, if you've used the Zoom webinar format, you may be familiar with this interface. You can ask questions of the panelists using the Q&A option at the bottom. You can also chat with panelists and or other attendees there as well using the chat function. We are recording each one of these presentations, and with permission of the presenters, we'll make those available afterwards on our North Central Climate Collaborative website. And just to thank a few others for our planning committee for this virtual workshop here this week. We've had Dennis Toddy with the USDA Midwest Climate Hub, Trent Ford from Illinois, our state climatologist from Illinois, myself, Julie Dahl from Michigan State, Miranda Meehan from North Dakota State University Extension, Peter Tomlinson from Kansas, also Kathy Gale from Kansas, and Hans Schmitz from Purdue. So we've had quite a diverse group kind of pulling this together, and I appreciate all their efforts to make this happen. Hans Schmitz did put some information in the chat box there for you. If you have any questions, you can reach out to him. And we also have Kathy on backside helping with technology if you have other issues. So please reach out if you have any problems along the way. I think I hit all the high spots here, Hans. Kathy, anybody else have anything to add? No? All right, excellent. We'll go into it. Trent, if you want to load up your slides. Trent Ford is the state climatologist for Illinois, based out of the Illinois State Water Survey at the University of Illinois. And he will talk first today about climate normals and kind of what that can mean and what we can use those for with the new updates that we've just seen here in the last month or so. So thanks, Trent, and take it away.
All right, thanks, Laura. So as Laura mentioned, my name is Trent Ford. I'm the Illinois State Climatologist based here at the University of Illinois in Champaign. And yeah, I'm going to be talking about the new normals, saying with my title, what is normal these days? And basically, we're going to talk about what we can and should be using them for, and certainly what we shouldn't necessarily be using them for or infer from them. And then give you some update information about, what the new normals look like, what things may have changed since the compared to the old normals across the region, and then where to find these said normals that everybody is talking about. So the word normal is thrown around a lot in climate, and unfortunately, it can be referred to in many ways, but the right way to use the word normal is to refer to the climatological standard normals, which were originally derived from the World Meteorological Organization, or WMO, to describe these averages of climatological data that are computed for consecutive periods of 30 years. That is how the WMO defines these climate normals and sets out a series of methods for different countries to follow in order to have these climatological standard normals that can be compared across the world. Now, the how they're actually calculated, I don't want to get into how the sausage is made too much, but basically the WMO recommendation, which NOAA and the National Centers for Environmental Information, who are in charge of coming up with the normals in the US, they follow the WMO recommendation to use 30 years of data and update these normals every 10 years. Now, the story behind the 30 years of data is really interesting. Actually, if you ask 10 climate scientists, they'll probably give you 10 different answers about why we use 30 years. But if you look back at the old documentation from the WMO, these standards were first decided upon in the 1950s. When we think about globally, many stations didn't have at that time more than about 30 years of data. So the WMO decided on 30 years as a way to make sure that we can come up with climatological standard normals across the world in a pretty consistent way. And they're updated every 10 years as opposed to every year, because updating them is quite an effort. I mean, we saw the new normals from NCEI being rolled out in May 4th. So, 4 months after the end of the year 2020, which is the last year compared to the normals. So this is quite an undertaking. And as a state climatologist, I'm somewhat glad they're not updated every year, because that would be an undertaking for me as well at the state level. So they're updated every 10 years at the end of each decade. Now, with that being said, our new normals are now over the period 1991 with 2020. With that being said, the WMO also recommends that the period between 1961 and 1990 is retained as a standard reference for long-term climate change assessments. And that's one big piece here. I'm going to continue to pluck that string of what the normals give us and what comparisons between the old normals, those from 1981 to 2010, and the new normals give us. And to give away the ending here, it's not a good representation of long-term climate change. So if we are looking to compare what our current normals are relative to long-term change, the WMO recommends using the period 1961 to 1990. Normals are not calculated at all weather stations. They're only calculated at weather stations that have a sufficiently long and complete data record. Now, if you go to the NCEI website that I'll reference at the end of my talk, you will see new normals, the 1991 to 2020 normals, for stations that don't have data all the way back to 1991. There are stations that have normals that are mixed from nearby stations. However, NCEI has flags on those stations that tell you that this isn't computed from an entirely serially complete record. And then the last question here, what do we use them for? Why do we even create normals? And so from NOAA, here at NCEI, normals act in really two different ways. First is a ruler to compare today's weather and tomorrow's forecast. You'll see on the news or from your local meteorologist, today's weather, today's temperature was 5 degrees below normal, or here in Champaign, it seems like the humidity's been well above normal the last few days. And as well as a predictor of conditions in the near future. So we think about something like outlooks for the 2-week period, 8 to 14-day outlook from the Climate Prediction Center of this probability of temperatures being above normal or below normal, or precipitation being above normal or below normal. So notice here that from NOAA's mouth, from the standard definition from NOAA, that normals are used for comparing today's weather and tomorrow's forecast and climate in the near future. Now, those words are used specifically to denote that normals are for planning and for understanding our current climate, and not necessarily inferring climate change that's happened in the past, nor climate change projecting what's going to happen in the future. And again, that's something I'm going to come back to quite a lot. So what's included? Lots of stuff, lots of stuff. When the initial, the first kind of rendition of normals first came out, it was really mostly just temperature and precipitation, average temperatures and total precipitation. But now with these new normals, there's a lot of more specific information that could be really helpful for folks. So I have this table broken out of what's included in the new 1991 to 2020 normals. By periods, we have the annual, seasonal, and monthly normals, and then we have daily normals, and actually hourly normals now for the new ones. Variables, as you would imagine, we have temperature, maximum, minimum, and mean temperature for annual all the way through hourly. Diurnal temperature range, which is something that we've seen changes in this north central region over the last 100 years or so. Normals for cooling, heating degree days, and growing degree days. And what's nice is that on NCEI you can get normals, the new normals for cooling and heating degree days is a standard 65 degree Fahrenheit base unit, and growing degree days from a standard 50 degree base unit. But you can also get growing degree days and cooling heating degree days from different base temperatures. So if you're growing a crop that requires or better aligns with 45 degree base growing degree units, that's also there as well. So you don't have to calculate that yourself. Precipitation, of course, we have total precipitation, snowfall, snow depth. And then we go to the hourly, we have some interesting normals for variables that tend to have more variability in the hourly resolution, like dew point, heat index, wind chill, pressure and wind, and then cloud cover. Along with the statistics, I mentioned the WMO, the World Meteorological Organization, defined these normals as averages. And yes, indeed, we have averages of temperature, average total monthly precipitation, things like that. But there's also higher order statistics like probabilities of first and last frost by date for given stations and areas. The growing season length, so the probability of a growing season length of X number of days, the probability of surpassing minimum temperature thresholds. So what's the probability of getting a minimum temperature below freezing or below 28 degrees Fahrenheit or below 0 Fahrenheit on these specific days. We also have quartiles, quintiles, and terciles. So you can look at not only what the normal average temperature for a day is, but what is the normal 75th percentile temperature for that day. And so you can look at variability and distributions. And then for hourly, we also have things like the 10th and 90th percentiles, the percent of calm wind occurrences, which is kind of interesting, could be useful for something like planning for spraying of herbicides and things like that. Modal wind direction, percent occurrence of sky conditions. So most of these variables are pretty easily retrievable for folks in the NCEI website. Some are a little bit more challenging to get, but at the end of the talk, I'll kind of go through where you can get these different pieces of normals. Okay, so I'm going to shift a little bit to talking about, okay, what should we use these normals for? Perhaps why should we care about them? And perhaps what we shouldn't really see these normals as, okay? So I'm prefacing this discussion with this figure here from NCEI, from NOAA, that shows the evolution of different 30-year normals for annual average temperature across the US. And these average annual temperature normals are expressed as an anomaly relative to the 20th century average. So areas that are blue, that normal was below the 20th century average annual temperature for that area. Areas in red is above that 20th century average temperature. So a couple of things here. We can see that in general, as we move from the beginning of the 20th century to our current normals, we have some spatial variability. You can see the quote unquote warming hole here in the Southeast US that has since disappeared in the new normals, or pretty much disappeared in the new normals. Overall, for most regions, we see a consistent or somewhat consistent warming trend when we see all of these normals lined up against each other. And in that way, we're sort of, and I reference up here, the top right corner, we're sort of looking at all of these figures as a movie, right? They're individual snapshots in time that when put together in sequence tell us a story, somewhat like a movie, all right, or at least when the movies before they went digital. So in this case, we can see when we look at them all together that increasing temperature trend that everybody is pretty familiar with across the US. However, when we take one of these normals out as a snapshot, it doesn't tell us necessarily the same story. We can't infer the same information. The same way that you wouldn't take a film reel of a movie, take one snapshot from that film reel and try to infer the entire movie from that snapshot, right? By doing so, there's going to be several mistakes being made. And I think this is where there's a bit of a dissonance in the climate community between what normals are and what they aren't. The 1991 to 2020 normal is a snapshot in time. This is our best representation of our current climate conditions. However, because it is just a snapshot, it does not give us a good message, a good idea of long-term climate change. Because indeed, our climate here in the North Central region is changing, both on the temperature side and the precipitation side, as well as variability. And so normals, one set of normals or comparison of two normals, for example, 1981 and 2010, our old ones to the new ones, they can give us information about how to better represent our current climate for year to year or maybe decade to decade planning, but they don't give a good overall depiction of long-term change. Okay, and so that is really where we need to use our normals. And transitioning here to the next slide, what the normals represent, what they do not represent. Okay, you may see figures like I'm showing you here on the right-hand side blasted all over, certainly all over Twitter, as well as different websites. This is showing the difference in average annual temperature and total precipitation on the bottom there, between the difference between the new normals, 1991 and 2020, the old ones, 1981 and 2010. And so you can see everywhere, if we just throw out the Dakotas there, mostly everywhere in the area has warmed, right? The temperature, the average annual temperature has increased relative to the 81 to 2010 normals. And most places have gotten a little bit wetter. However, without the context of understanding what these normals represent and what a comparison of one normal to the next normal represents, one could very easily infer that the changes depicted in these maps are representative of changes over a longer time period, which is just simply not the case. The Dakotas are getting warmer over the last, or have gotten warmer the last 150 years, despite the new normals being slightly less than the old ones. And so what that means is what these normals represent is a summary of the last 3 decades climate. That is something we can hold up and say, the last 3 decades climate, here's what these summarize. So information that you can glean from these normals is what is the expectation for the average temperature on this day, on this month, on this season, in this year? How much rain would I expect to get this next 4 weeks or this next month? Right, and using the last that 30-year period that's most recent gives us the best snapshot of that climate in time, with our knowledge that yes, the climate is changing. But if we were to take the entire record to summarize our climate, as I'll show in just a second here as an example, what that may do because of our changing climate, it could falsely represent climate conditions that aren't really relevant to today's climate. So yes, it is a summary of the last 3 decades climate. It is not necessarily a representation of long-term change driven by global warming. Now, don't get me wrong, there are pieces of anthropogenic or human-induced climate change in these normals, for sure. I can go back to that map I showed you of the progression of temperature. That is a snapshot of, or that is a representation of climate change. So there is that piece of that in there. However, when we compare the old normals, the 1981 to 2010 normals, with that from 1991 to 2020, what we're essentially doing is comparing the 80s with the 2010s, because the 90s and the 2000s are in both normals. So we have to understand that when we only compare periods of 10 years or even 30 years, we heighten or enhance the effect of interannual, year to year, and decade to decade variability from things like the El Nino Southern Oscillation, and so the Pacific Decadal Oscillation, things going on in the Atlantic and the Arctic. When we compare those short periods, relatively short periods of time, that variability is enhanced. And therefore, we may drown out that long-term climate change signal, which is, again, another reason why these sorts of changes aren't really good representations of long-term climate change. And then what these normals are absolutely not is a projection of changes to come. And I'll show you that in a little bit of a good example of why we should not infer that the difference between, certainly the difference between the 1980 2001 to 2010 normals and our new normals are not necessarily projecting of things to come. So the advantage of doing normals, why do we do them in the first place? The updated normals are theoretically more representative of our current climate than old normals, and therefore can be better for planning in our current climate than if we were to use the entire period of record or an earlier normal. The disadvantage, though, is that updating the normals can obscure long-term trends in the risk of extremes. And that is a really important piece to understand, that if we're thinking about the risk of, let's say, extreme heat to the city of Chicago and how that has changed and is projected to change in the future, using a 30-year period of time is not the best way of going about doing that. So the nuance and context are really important. Unfortunately, nuance and context are very difficult to get across when you only have 140 characters. So that's why I kind of say when using these normals and comparing differences on places like Twitter or short kind of website blogs, it can be really challenging. And so we need to think about that when we're communicating these changes. Okay, so I'm giving you two examples, one in which showing the importance of why we need to understand our current climate in the context of long-term climate change, and the other showing you an example of problems if we infer long-term climate change from a change in normals. So this one here is talking about the date of the last spring freeze and corresponding growing season length. So growing season length, which I just defined here as the time elapsed between the last spring freeze and the first fall freeze, is increased across the region since the start of the 20th century. All right. So for example, because Laura's moderating, 1991 to 2020 average growing season. So our normal growing season length of our new normals in Aberdeen, South Dakota is a week longer than the 20th century average. And that is describing that long-term climate change. I can show you here on the right-hand side, this figure is showing the trend in the last spring freeze date in Northern Illinois between 1951 and 2020. You can see that downward trend. The median date of last spring freeze in Northern Illinois has trended about 1 day earlier in the spring per decade since 1950. So about a week shorter or a week earlier. And of course, what that means is with the whole distribution shifting, what we consider a late spring freeze isn't as actually late in the spring as it was around the turn of the 20th century. And so overall, it reduces the late spring freeze risk across the region. However, if we were to just, for example, give that information or use a long-term record to say we need to encapsulate this change, so we need to take the entire period of record to summarize the normal quote unquote last spring freeze, we could run into problems. So what I'm showing you here, these two maps show across the region the median date of the last spring freeze. I use 28°F there for the last spring freeze based on the 1961 to 1990 normals on the left and the 1991 to 2020 normals on the right. And there has been some change, quite a bit actually over that time period. So for example, the new normal, the 1991 to 2020 last spring freeze date for St. Louis, Missouri is the same as the 1961 to 1990 last spring freeze date for Jonesboro, Arkansas, which is several hundred miles to the south. So we've seen that, again, that moving of that last spring freeze date earlier in the year. What this means is that if we are communicating these important variables to stakeholders, we need to make sure that they're representative of the current climate in which we're operating. So therefore, using the most recent 30-year period, that 30-year normal, gives us an idea for, okay, yes, we have changed. We've seen these spring freeze dates changing, but we need to make sure that we're representing the fact that spring freezes are happening earlier in spring, or that last spring freeze is happening earlier in spring. And therefore, we need to communicate that information for planning decisions, for example, in the spring. On the flip side, I have example number 2, which is summer drought in Iowa. This figure on the right-hand side stuck out to me when I was going through things. So what this is showing is the change between the 1981 and 2010 normals and the new normals for July precipitation. It's expressed as a percent change. So there's some mixed signals across our region, not really a whole lot going on. I mean, July hasn't necessarily gotten a lot wetter, a lot drier since the 1980s, but we do see that dry signal in Iowa, in west central Iowa. Overall, new total July, the new total July precipitation normal in western and central Iowa decreased about 10 to 20% from the previous normal, which is about 0.3 of an inch, which was kind of interesting to me. So I took the long-term running station in Ames, Iowa, and I plotted the old 1981 to 2010 normal monthly precipitation and the new normals from Ames. And we can see they track pretty well. I mean, things haven't changed considerably, but we can see this dip here in July. Right. And certainly, I mean, if you are agricultural stakeholder, farmer around West Central Iowa, and you see this figure on the right-hand side, and think to yourself, well, we just went through a pretty nasty drought last year. Things aren't looking great this year. And now you're telling me that based on the new normals, our precipitation in July, that really important period of time for crop stage reproduction, is decreasing. That could be a problem. Again, this is the importance of communication, the context of this. And I'll show you that here. What I'm showing you here on the right-hand side is a plot of total July precipitation in central Iowa going back to 1901 to the present, to 2020. And then these different colored lines shows the 30-year averages or the 30-year normals from our newest normal, which is in green on the right-hand side, all the way to the, orange on the right-hand side, all the way to the 1901 to 1930 normal. And what we can see here in central Iowa is that starting in the 19 teens, we see this consistent increase in 30-year normals coming all the way to the 1981 to 2010 normal. However, the 1981 to 2010 normal, because of some very, very wet Julys in the 1980s and early 90s, was much higher than any previous normal. The new normal, the 1991 to 2020 normal July precipitation, is still higher in central Iowa, still higher than any other previous normal except our previous one, the 1981 and 2010 normal. So we still see that long-term increasing precipitation trend for July precipitation in central Iowa. It's just that the 1980s and early 90s were so wet in central Iowa that it pushed that 1981 to 2010 normal very, very high. And we're kind of coming back to earth on that. And so therefore, this is the context we really need to be communicating here, is that, again, a difference between two consecutive normals, or just taking that snapshot of that one normal, we should not infer, and that normal does not imply any sort of long-term change. So again, if I look at this map, I say, gosh, it's getting drier in Iowa in July. That's not good. But in fact, the long-term trend is we are still wetter in central Iowa in July than we were at the turn of the 20s. That is really important to understand. Okay, so with all that being said, I want to wrap up things by just showing you a few maps of the difference between the 1981 to 2010 normal and the 1991 to 2020 normal, just to show you how the new normals have evolved. Now, again, we need to have caution here that these differences do not necessarily represent long-term change. It's just an idea to get, as you've been operating with these old 1981 to 2010 normals for a while now, how things may be changing in the state as far as the new normals are concerned. So the first one is maximum temperature. Just break this down by month here across the region. So red areas are areas where the new normals are a bit warmer than the old normals, and blue, as you would imagine, where they're a bit cooler. So you can see here, it's no surprise to anybody who's been operating in the Dakotas, Minnesota, and Iowa that February maximum temperatures, and then here, interestingly, April and May maximum temperatures have actually cooled a bit since the new normals. And that's just the result of some pretty recent, very cold April and Mays. And then we see some warming in the southern part, especially warming in the fall here, these maximum temperatures. I look at September here and I think about the year 2019 in Illinois, for example. We had folks that were very delayed with planting that were actually able to get their corn and beans to maturity because September was very warm. And so we are seeing that those September maximum temperatures have increased a bit in the new normals. And then December sticks out like a sore thumb. I was actually updating the normals for Champaign here for our almanac. And just in Champaign alone, the December maximum temperatures for the new normal is almost 3 degrees higher than the old one. And so I haven't seen a good explanation. Of course, these normals just came out in just about a month ago. But I haven't seen a great explanation for December, but it's drastic actually to see December compared with the adjacent months of November and January, where we see that widespread increased temperature. Minimum temperatures sort of follow the same idea here, increases in minimum temperature, especially in the summertime and the winter, or excuse me, I guess not the winter, the fall necessarily. But again, we see this 2 to 3 degree increase from the old normals in December in the upper Midwest. And so we're seeing overall increasing minimum temperatures there between the two normals. And then some derivative products here. So this is showing the change in, between the two different normals in the days with the minimum temperature below 0 degrees Fahrenheit. So we're thinking about these as very cold nights. So we see in blue here is an increase in very cold nights relative to the old normals, and the red is a decrease. As you would expect, okay, minimum temperatures decreasing in February and to a lesser extent March in the Dakotas and Minnesota. But again, December here is sticking out where parts of Wisconsin and Minnesota, kind of that Duluth to Eau Claire corridor, have anywhere between 2 and 3 fewer cold, very cold December nights. It's where the temperature gets below 0 degrees Fahrenheit in these new normals relative to the old normals. So seeing some pretty large changes there in December. On the flip side, maximum temperature, this is what I consider cold days, the maximum temperature days when the max temperature doesn't get above freezing. Similar things here, actually quite an increase I'm sorry, my color bar is flipped around here. My apologies. Red here is a decrease in those very cold days. Blue is an increase. So we see an increase again in February, especially in that, the Red River Valley up there, and again, a decrease here in those cold days in December. Now on the flip side here, some heat statistics. So these are the change in the days, the number of days, the maximum temperature exceeding 90 degrees Fahrenheit. And there's an interesting pattern here that actually kind of agrees with some of my anecdotal evidence, especially in the late summer. So we see here in the southwest part of our region a change where we have more 90-degree days in June relative to the 1981 to 2010 normals. Not much change in July, actually a little bit of a decrease here in the northwest part. But August, pretty much across the board, either no change or a decrease in those days above 90 degrees Fahrenheit, where actually September was the exact opposite. And indeed, over the last 3 years here in Illinois, our September average temperature has actually been within a degree. And actually last year it was warmer than our August average temperature. So that's actually been a pattern that's been of interest here. And it kind of, again, goes back to the extension of the growing season into September, especially where we're not only seeing an increase in average temperature, but we're also seeing that increase in days getting above 90 degrees, those hot days, quote unquote. And then, something that is often overlooked are those very high minimum temperatures. So this is showing the change in the days with the minimum temperature not getting below 70 degrees. And interesting here, when we add up the change in June and July, we see that here in the southern part of the Midwest, we have 2 to 5 additional very warm nights in June and July in the southern Midwest. And when we add up all these months together, we're seeing an increase of about 7 to 8 additional very warm nights in the warm season in places like southern Illinois, far western Kentucky, and the boot heel of Missouri. And so, of course, those have their own implications when the minimum temperature doesn't get below 70 degrees, both to plant as well as human health. But that is an interesting pattern to see there as well. Growing degree days, as you would expect, based on the last couple of years, slight decrease in growing degree days in April and May in the northern part of the region. And then as we expect here, an increase in our core summer months, and an increase in September. And again, this is speaking again to that extension of the growing season this September that we've seen, and it's pouring it out here in that change in the normals. Okay, so wrapping it up here, last bit here, probably the most important slide, and I'm going to end on it here. I've been talking a lot about the normals, but where can I find them? That's a good question that I asked myself. So NOAA, NCEI, the typical normals website is there. I don't know if Kathy or Laura mentioned this, but I'm happy to share these slides here for folks to go to. If you Google new climate normals, you'll probably find this site, but you may find some other sites. So this one's a good one to go to, and you can access most of the essential climate normals: temperature, growing degree days, precipitation there. The High Plains Regional Climate Center is working on a custom climatology tool. It's up, but it's also being kind of a work in progress. It's a pretty neat tool to go check out there at their website. And the Northeast Regional Climate Center, we also have gridded normals, which are apparently supposed to be released to the public very soon, but they have a gridded normals mapper, so you can map an entire region and how those normals have changed there. And that's also a work in progress. They'll be adding new features on that as well. And then probably your best, a little biased here, but probably your best source, especially if you can't find the information about normals or just climate change in general, your local state climatologist office. And when I get asked by the media, give me your website, I don't think I can even remember my URL, but a good Google of Illinois State Climatologist Office or enter your state here, State Climatologist Office will get you where you want to be. The last tool I want to plug here, this has some information about the new normals, but also just in general, a good way to explore your region's climate. And it's pretty user-friendly is NOAA's Climate at a Glance tool. So that's at this URL here. And if you're just wondering how has this changed, or what does this look like, this parameter, temperature, precipitation, whatever it may be, that's a good one to go to. So with that, I want to thank you for bearing with me through all of this information. I'm happy to take any questions if there's time to do so, and I'll turn it back over to Laura. Thank you again.
Right, great. Thanks, Trent. That's a great presentation. We do have a short poll, and this is asking about Trent's presentation. So we appreciate you, and he will get that feedback. That's all anonymous. We did have a question in the Q&A, Trent. Let me find it back here. I think you may have addressed it, but I'll ask it again. Okay, here from Brian. He asked, and this is from way early when you were talking about normals versus trends. I had thought the 30-year threshold was the minimum data period, not the standard to compare. For example, if a 50-year data set was available, it should be used.
That's a good question. Yes, that's a good point of clarification. So, yeah, the 30-year was thought of as the minimum, although, again, the period of 30 years was actually determined because that was the sort of common denominator among stations back in the 1950s of we have at least 30 years at most stations, so we should use 30 years. Certainly if you want to summarize a region's climate, you can use a longer data record. But again, depending on the parameter you're using and how much that parameter has changed over the last century and a half, and how quickly that parameter has changed, it may behoove you to actually use that 30-year period as opposed to a longer 50, 80, 100-year period. That's kind of what I was getting at with the spring freeze dates, whereas using time periods that earlier in the 20th century may actually, or in my case, I use the example of 1961 and 1990, may actually not represent the current climate because of that rapid change in that spring freeze day. So that is important to consider. Also to this point, NCEI, that's something I didn't mention, NCEI not only has put out 30-year normals, but this is the first go around where they've actually produced 15-year normals as well. And this is getting at the idea that folks for like energy demand planning really need to use the most up-to-date information. And so using the last 15 years gives them an idea, is again, theoretically more representative of our current climate than using a longer term period.
Yep, that sounds great. There's another comment in the chat here. And maybe you can see that from Brad Johnson. I recently read that some of the cooler new normals seen in the upper part of the region may be associated with increased cloud cover associated with increased water vapor in the air in the region. Is there anything to this idea?
Yeah, that's a good question, Brad. There's a lot in a lot of I suppose theories about what's going on in the northern part of the region, and that is one of them where we see increased humidity, increased water vapor in the air. That is due to changes in land cover as well as increases in overall temperature in the winter and spring, for example, that can make for depressing those maximum temperatures. And that's something we've seen here in Illinois, even farther south, where maximum temperatures are increasing in Illinois, but not at the same rate as minimum temperatures. However, again, when we're looking at these 30-year periods, the role of decadal and interannual variability from large-scale features like sea surface temperatures in the Pacific and the Atlantic do play an important role. And so there is that teleconnection, as we call them, the connection between the patterns of sea surface temperatures and pressures all across the world in a more of a regional climate. Those teleconnections play an important role in that as well. So I don't know if it's necessarily pointing to one thing and saying this is why those temperatures are those normal temperatures are a bit cooler in places like the Dakotas. It's likely a mix of many different forcings, and there may be that role played by the increasing cloud cover as you allude to there.
Mm-hmm. All right, Trent, we have a few more questions in the chat, and I'll ask you one more, and then maybe you can respond to the others in the chat so that we
Sure.
can get to Martha next. So Hannah asks, why do you think the December charts are such a dramatic change while the rest of the months tend to be more moderate?
That's a really good question, Hannah. And I'll let you know that it's been bugging me since I've seen it. And actually, I like I mentioned, I updated the daily almanac here in Champaign and saw that big change in December. One thing I didn't show was December snowfall, which for the southern Midwest has decreased by, in some cases, 2 to 4 inches since the new normals in December snow. So that's something that it's bugging me enough that I'm going to have to start looking into it a little bit. So I haven't seen anything that can explain necessarily why that's the case, but that's something that hopefully we can look into a little bit more, because you're right, the change in December is so much larger than even the adjacent months of November and January. It speaks to something kind of interesting going on there.
All right, great, thanks. I do see the other questions from Crystal, Kevin, and Chris. So Trent, you can respond to those in the chat or the Q&A. And we'll go on to our next presenter. I believe